All right, good morning, everybody. Today was Codeforces round 661. It was a Div3 round. There was like some queue issues and it was delayed for 15 minutes. And then also I had a couple technical difficulties while recording the video. There were basically issues with the webcam, and then it wasn't easy for me to just like show only the screen instead. So basically, I probably won't upload my competition in the contest. I did solve the set, but usually, like, I know there are several people who pretty much use my channel as easier to understand editorials. So I'll definitely go over the problems so I don't leave you guys hanging on that end. So we'll talk about how to do all the problems here, and then if you didn't solve some of them or want to upsolve them, feel free to do that after seeing this, or you can just go read the regular editorial. That works too. Anyway, let's start with the easiest problem, problem A. So I'll also show my code in these if you're interested in the code part as well. So you're given some array, and you can, during any turn, choose two indices and delete whichever one has a smaller value. So in this example here, you can delete this 1, for instance, and now you have two 2's left. You can delete one of the 2's. You want to make it so that there's only one element, but the restriction on your move is if you have two elements that differ by more than 1, you can't pick both of them. So you have to pick two elements that are at most 1 apart, or they can be the same, and you delete the smaller one. Now, it should be pretty clear that you want to not create gaps within the elements, so it's always beneficial to remove the smallest element at each step, if you can. Once you do that, then the best thing you can do is just see, is there any gap already? Because you wouldn't create any gaps, you only delete the smallest things. So basically you want to see, are there any two elements, if the array is sorted, that differ by 2 or more? And the code for that is pretty simple. It's just a matter of, you sort the array, make sure not to use arrays.sort if you're using Java, and then once you do that, you can check all pairs of adjacent elements to see if they differ by more than 1. If you use arrays.sort, there's a break case that makes that n squared. So that's an easy issue that you might have. Well, actually, never mind, that's fine, because n's small, so n squared is fine. Yeah, all right, so that's problem A. Let's look at problem B. This was, I guess, similar in the idea of, like, you just look at the whole thing, make the greedy observation, and then do that. But I guess it's a Div3 contest, so the problems are going to be pretty easy. But yeah, so you've got 3 different moves you can do. You can decrease the first number of some pair, you can decrease the second number of some pair, or you can decrease both numbers. And then you want to make it so that all of your pairs in this array are the same. They have some flavor text about candies and oranges, but really that's the entire problem. So basically, in this group, we need to make all of these equal to 3 on the top and 2 on the bottom. To do that, we can decrease this 3 here by 1. This is probably a little small. Yeah, we've got a whiteboard, right? Why not even use it? So you've got the pairs 3, 3, 5, 2, and 6, 3. Now, since we can only decrease them and we want them all to be the same, we're going to need, at most, the bottom will be a 2, and at most the top will be a 3, right? So basically, what we need to do is we need to turn all of these into a 3, all of these into a 2. If we do some operation on this, we can decrease both. Well, we can decrease either one of them, or we can decrease both. We don't need to decrease this top one. So the number of moves will just be the number of moves it takes the bottom one to turn into a 2, which is just 1 move. So we'll have to spend 1 move on this pair here. Then for this next move, we have to turn this into a 2, which it already is, and the top one into a 3. So this will be 2 moves. And then for this last move, we have to decrease both of them. So as long as they're both too big, we'll take from both of them. And so after the first move, we'll have 2, 5. Then we'll just want to decrease the top one. So we decrease the top one twice, then we have 2, 4, and then we have 2, 3. So the number of moves here will be the max of 6 minus whatever this number is, and 3 minus whatever this number is here. So it's just the max of 3 and 1. And that gives us a total of 6, which is the right answer for that sample. So the TLDR is we need to find whatever the minimum in this array is. That'll be what all elements will end up being. Same thing with this array. The minimum of this is what all the bottom ones will be. Then once we have that, for each pair, whichever takes more moves is whichever they will be set to. So we use the maximum there. The code for that is pretty simple. Just looks like this. We read in our two arrays. We find the minimum in the first array and the minimum in the second array. And then after that, we look through each pair, and then we add up whichever half is bigger, getting the top element right or getting the bottom element right. The other element we can subtract 1 from as many times as we want, but then since we have more steps in the other half, we'll just keep it at 0. Keep subtracting 0 for the rest of them. All right, cool. That's problem B. Let's look at problem C. Boats competition. So in this problem, you have a bunch of pairs of people, or you have a bunch of people rather, and then you want to split them up into as many pairs as possible, where each pair has the same weight, and obviously you can't put the same person in more than one boat. So each person you can only use once. Yeah, the important thing to notice here, for me at least, was that n was very small. So I just did a very naive approach here. Basically, since you know each person is between like not $1, each person's worth $1. Each person's between £1 and 50 pounds. That means that the total weight of a boat is somewhere between 2 and 100 pounds. So if you know the weight of a boat, then you know what people each person can match with. And once you have that, you can do a greedy. Since all people of the same weight are the same with respect to this problem, like there's no difference between two different people of 1 pound, you might as well just use the first one in the line if you're matching someone with 99 pounds and you want a total of 100. So yeah, that's the idea. So I guess there isn't really much to explain there, but code-wise, what we can do is brute force the total weight. Once we know that, then we'll count how many people we've seen of each given weight. We'll also count how many pairs we've made. We look through each thing in the array. If the total weight is bigger than this element, or if the total weight is less than this element, then this person can't fit in the boat, right? So we have to not have this person at all. Basically, this person would be heavier than the total amount the boat needs to weigh, so obviously it's not going to work with them. It's to avoid array index out of bounds exceptions here. But basically, the total weight minus this weight is the other person this person would match with. If we have one of those people in the spare box waiting to take, then we'll take them and pair them with this person. If we don't, then we just take this person and put this person in the box. At the end, we just, among all different possible weights that we could use, we just take the biggest of them and then print that answer. So we take the max over all of those. All right, that's problem C. Again, pretty straightforward. And problem D was quite quick as well. The idea with problem D, these are very similar in that the only thing that matters here, in the last one, the only thing that mattered was the weight. I guess that's it, because they're just numbers, really. In this one, the only thing that matters is the last digit. So if you have a bunch of subsequences, and then you're about to append a 1 to one of these subsequences, then you can append it to anything that has a 0, assuming you want these alternating 0, 1s to be the subsequences that you make. So basically, let me quickly go over the problem. You're given some string, and you want to split it into subsequences. So subsequences means you delete some characters, right? Basically, you want to take the string and split it up into different groups. So maybe split it up into 3 different groups by picking 3 characters in a row and then putting that as group 1, picking 5 characters in a row, that's group 2, picking 1 character in a row, and that's group 3. Those are your 3 different groups. And you want to make sure that you keep them in the same original order. And also, each element in the original string gets picked at most once, or exactly once, rather. And you want to see what's the fewest number of groups you can make that are of this form so that you cover the entire string. We can do a greedy for this. So we can say if we don't have any more groups where we can put a 1, then we need to create another group. If we do have a group we can put a 1, it isn't really necessary that we create another group now, because it's better to have one fewer group. Maybe we can fill it with a 1 or a 0 or whatever we want later. It's better to have not create that extra group than if we can replace something with just a 1, because we have less freedom in that case. So yeah, so basically we just keep track of how many groups do we have that we can place a 1 in front of, how many groups do we have we can place a 0 in front of, and how many groups do we have total. Then if we see a 1, we try and place the 1 in one of the groups we can place a 1 in. If we see a 0, we try and place the 0 in one of the groups you can place a 0 in. And if you can't do one of those operations, then you have to create a new group. So again, it's not really super explainable with a whiteboard, I think. But we'll look at the code because I think the code is kind of helpful. So I keep this list. I use an array deck, but you could use a queue or a stack or whatever you want to keep track of which piles have 0s and which piles have 1s. That's the idea. Then next, this is just the answer that I ended up printing out. I also keep track of how many groups there are in total. So now, if I see a 1, the logic for 1s are just reversed. But if I see a 0, then if there are some piles that I can place a 0 in, then I just place it in that pile. So I place it in the pile, and then I say whatever that pile is, it used to end with a 1. Now it's going to end with a 0, which means now you can place a 1 at the end of it. So I add that pile as like piles that you can place a 1 at the end of now. Then I also mark my answer. Otherwise, if there aren't any piles, then I create a new pile. So I increment the number of piles. I set my answer for that. And then I also add that to the list of 1 piles. So now if we have a 1, we can place a 1 after this 0. Yeah, okay. So that's the idea. You do the same thing with 1s. You just flip them with 0s, and then at the end you print your answer. Okay, that's problem D. Now problem E is where things got a lot harder, I felt. And I actually struggled with problem E a little bit. So instead, I'll talk about problem F first, and then I'll talk about E at the end, because I think F is actually, it's pretty classic. Like if you've seen something like it before, you should be able to get it pretty quickly. It's also a really good thing to practice, I think. So in problem F, you have a bunch of segments on the x-axis, and you want to choose as many segments as possible so that all segments, either one contains the other, or they're disjoint. In other words, you don't want any segments that look like this. So you want to basically delete as few segments as possible so that all of the segments that you have left over are entirely disjoint. In this case, you could delete just this segment here. And now, if you look at any pair of segments, maybe we look at this pair here and this pair here, these two are, one covers the other. And then if we look at this pair here and this pair here, they're separate. So yeah, that's the problem. You want to pick as many of these segments as possible. And importantly, the number of segments is less than or equal to 3,000. So not that many segments. You can do an n squared. Yeah, so the first thing you can do is you can coordinate compress. So the coordinates they give you go up to 10 to the 5th. There isn't really any reason for that. So you can coordinate compress so that the coordinates go up to, because like all that matters is like the relative positions of these endpoints, right? So you can coordinate compress and now the coordinates go up to 6,000. And we'll do like a 6,000 squared plus 6,000 times n. This will be our final dp runtime. So n squared plus n times 2n, I guess. So basically it's just n squared times constants. Yeah, so now here's the idea. We're going to do a dp assuming like we have some range that was the last relevant placed segment. So initially the segment that was placed covers the entire range, but then after that you want to pick some other segment. And we can always pick the segments from like biggest to smallest basically, or in other words from left to right, tie breaking by right endpoint. So we'll think about it in kind of a different way though. Let's think about it as like, what's the last segment that we placed that's relevant? And the DP will try all ways of placing whatever segments we want, but it'll never place a segment that crosses the last relevant segment. And it'll also only place segments that are like within this last relevant segment. So it's basically DP, here's like what it actually looks like, DP at some segment equals the max answer if you're entirely within the segment. Now, when I say segment here, I don't mean one of the segments that you're given in the input. I mean any segment at all. So really, there are n squared of these, because it can have any left endpoint and any right endpoint. All right, let's look at what this looks like maybe for this, like how it would get the right answer for this case. We'll add this back in, so it's less trivial. So initially, the answer will be this DP state right here. So it'll add 1 for taking this segment. Now, after that, it'll look at some other segment. There's some other segment it has to take. Maybe it takes this segment here. So what we can always do is we can always just choose not to pick anything at this left endpoint. So we can, this DP transition is the same as this DP transition right here. And then once we're at this left endpoint here, we want to look through all segments that start at this left endpoint and will fit in our current range. So this segment starts right here, it'll fit, so we can pick it. When we pick it, we split it up into 2 groups. So here's the first group, stuff that fits entirely within here. We also split it up into another group, which is stuff that fits entirely within here. And then we want to calculate the answer for these 2 parts. So that's basically the idea. Yeah, okay. So if we know what this transition is, right? The transition is just pick some other segment that starts here. And I'll get to runtime in just a minute. You might think this is n cubed, but it isn't actually. It turns out it's n squared. But yeah, so we have whatever our left endpoint is. Our transition is we can either make the range smaller, or we can pick some segment that hits one of the endpoints. Once we pick that segment, after that, if we're going to pick this segment for sure, if we know we're going to pick this, then all of the other segments we have to pick either need to be entirely inside of this segment, or they need to be separate from this segment and after it, like that. So those are just 2 other DP calls. So yeah, all right. Why is the runtime okay? So here's like the initial argument. Well, you've got n squared states, and each of your transitions looks at all of the segments that are given an input that start at a given position, right? And there might be order n of those. So that might be a problem, right? Because this would be n cubed. But it's not really n cubed. In total, it's n squared. And the reason for that is that each one of these segments will only be used by order n different states. So you have n segments. Each segment is used by n states, which means in total, the total number of times that all segments are used is n squared. As like your total transition over all states is just n squared. Total number of states is also n squared. The n squared things that, if you've got this segment here, the n squared ranges that might use this are you might use this one here and like any of these positions here. So that's order n. You also might use this endpoint here and then all of the things like this. So that's another order n. All right, very good. So now what does the code look like? It's actually not as bad as you would think. And I won't like totally go through all of mine because it's a little bit long. And I don't want to make the video too long because I might bore people, right? So yeah, so I won't go through it too long. But you have to be careful with, like, there's one case that I didn't consider originally. And I failed samples, but like it was really easy to find. And that is the way I wrote my DP. I didn't want to count ranges. Like if this was the range I was counting, I didn't want to count segments that covered this entire range. I thought that would make it easier. Maybe there's a better way of doing it, I'm not sure. But I didn't want to count these segments. But I had one issue, which is when I picked some segment, then I would look at this range here, which would be fine because I wasn't causing a loop, because I wouldn't consider a segment that covers the entire range. But I would also look at, maybe this was the range I initially covered, right? I would also look at this range here, and then I would recursively solve this, and then also solve this. So that seems fine. There's one issue, which is it's possible that there is another segment here that now you won't be able to take because you're looking at its range exactly. So in order to fix that, I added 2 sometimes. Like I add 1 for this one, and I also might add 1 for this if I cover it exactly. Yeah, that's the idea. Okay, very good. Last problem is problem E. And I'll talk about both of them. But basically, the only difference between them is that in E2, so in both problems, you've got some tree. Maybe it's like this. And your edges each have weights. So maybe this is like 5, this is 7 to 4 or something. And you look at all paths from the root, which is node 1, all the way to each leaf, like this. So there are 3 different paths. We want the sum, oh, I'm missing a weight here. Maybe this is 100. We want the sum of these weights to be less than or equal to x. Or less than or equal to s, I think. So we have to modify the edge weights in such a way that this happens. The only modification we can do is we can pick some edge. Some edge. My handwriting is atrocious today. Pick some edge, weight divided by equals 2. So we can take some edge, half its weight, floor it, basically, after we divide by 2. So we could make this 5 into a 2, for instance. That would be one thing we can do. We want to make the weight as small as possible. In problem E1, you want to do this as few times as possible. But in problem E2, there are certain edges that count as 2 moves. So you want to take as few moves as possible, but for E2, there are some edges that it costs twice as much in order to half their weight. So yeah, all right. So that's the problem. How do we actually go about doing this? Yeah, there we go. That's the issue we had before the webcam just kind of like got stuck. So just checking it to make sure it's all right, but we're looking good. So okay, for this problem, the first thing we want to notice is that if you look at some edge weight, we can always figure out how many times this edge weight will be counted. In this case, it's counted twice, so it's just 100 times 2. And the number of times it's counted is just the number of leaves in this node's subtree. So we can pre-compute all of that with a DFS. That's easy enough. We can do that for all of these other nodes as well, or all these other edges as well. We can just see how many times is this edge going to be counted. Once we've done that, we no longer really have a tree problem at all. It's more of just like a knapsack problem. We want to pick the fewest number of things in order for the total weight to be minimum. Now, yeah. So I guess there are a couple ways of doing this. The easiest way that I thought was just to use a priority queue. You can just look at this 100, like put all of these numbers in a priority queue. But for the 100, you want to weight it twice as much. So 100, if you have it, the benefit of having 100 will be 100 minus 100 over 2. But also you want to multiply this by the number of leaves in the 100 subtree. So this would be equal to 50 times 2 for the 2 leaves, because you get the benefit twice. You always want to take, if you're going to spend $1, you always want to spend that $1 on whatever thing helps you the most. So for problem E1, that's the solution. We just have this priority queue, and within this priority queue, we just repeatedly take the best thing, remove it, and then we keep going until we have the right total. The code for that is pretty clean, so I can show you that. Well, actually, I can't show you it. You can view my submission if you'd like, because I erased it to solve E2 in contest. But then for problem E2, it gets a little harder, because we don't necessarily know whether we want to delete a 1 or delete a 2, right? It's a difficult choice to make. So we can solve that in a slightly more interesting way, I guess. What we can do for that is we can split the problem up into 2 groups. We'll solve it first on the groups of 1s. Maybe those are these ones here. Each of these circles represents some edge where we can get some number, we can decrease the cost by some amount if we have this edge. We also have a bunch of 2s. And if we decrease the cost for one of the 2s by some amount, or if we have the edge, we decrease one of the costs for 2s by some amount. But each of these cost like 2 moves. So that's the concerning part. Each of these cost 1 move. Now, if we do something multiple times, we might delete it, and then we'll put it back. But when we put it back, it'll be worth less. So it'll be somewhere later on in the list. So it shouldn't actually be an issue yet. Yeah, okay. So that's the idea. So now what we can do is if we did this problem greedily on the 1 moves, we would get some answer. We would also get some answer for the 2 moves. There are a bunch of ways you can handle this now. You can brute force how many 1s you do, and then you can sweep through this 2 move way and figure out how many 2 moves you need to do in order to accompany that. You can also do it greedily just without even a sweep, which is what I did. And the idea behind that is if you're going to spend $2, you always want to spend those $2 either on the best 2 1s or on the best 2. You're either going to have 2 edges. It might be the same edge twice. You might have this edge twice. It's kind of hard to tell. But you're always going to spend either both of those on a 1 move or on a 2 move. Because I guess there are only 2 ways to distribute like integers so that they sum to 2, either 1 plus 1 or 2 plus 0. Because you can't pick negatives. So now, yeah, you want to find the best way of doing that. So if you're going to spend $2, you're like, okay, do I spend this or do I spend this? Whichever one is more beneficial is the one I'll do. And that's pretty much the solution. There are a couple things to watch out for. The first thing is if you take some group here, you might be able to take just 1 more instead of taking 2. And that will be something that like you're able to solve with just 1 more, right? So the answer will be like some multiple of 2, but you might have to add 1 at the end. This is one way you might add 1. You might add a bunch of groups of 2. Maybe you take like this 2 here, you take this 2 here, you take this group of 2, and now you can add just 1 more thing, and that'll have you reach your sum that you want. So that's one thing you have to watch out for. The other thing that you have to watch out for is it's possible that it's a good idea to take these ones right here, right? Maybe you take these 2 groups of 1s, sure, but then at the end you take this group of 2 and this sets you over the bar. It's possible you didn't actually need to take one of these 1s. Now, you definitely need to take at least one of them, but it's possible you didn't need to take both of them. This one here we might be able to delete. We might be able to like undo that move. So we can store how much benefit we got from the last time we have some edge for a cost of 1. And at the very end, we can consider, okay, if we didn't actually do that, if we go back in time and undo that move, because maybe it was unnecessary, then would that still make our answer valid? And if so, you can decrease your answer by 1. So I'll just show you my code for that briefly. So here's the idea. First I do a DFS, then I store each of these items, which store how many leaves they have, which is like basically their multiple, the parent edge weight, and whatever type they are. And I've got 2 priority queues, 1 for things that have a cost of 1, 1 for things that have a cost of 2. Then as long as the current sum is too big, then I have to delete something. So this is the case in which I delete just 1 thing, but it's also possible that maybe I delete 2 different things. And I look at that, I consider that as well. So either I delete 2 1s here, or I delete 1 2. And that's the best I can do. And then finally, this is the other thing, which is once I've reached my total, it's possible that I took 2 1s when really I only need to take 1 of them. So I compensate for my answer by subtracting 1. I undo that move. That's the solution. There's a bunch of like logic with priority queues here that I had to be careful with. But yeah, those are straightforward enough, I would say. And they're pretty simple. You just have to be careful. Where's the one hard one? Here's the hard one. Calculating the benefit of taking 2 things without actually removing anything from the priority queue. I struggled with that for a bit, so the logic was kind of complex. It might be easier just to do it once with 2s, do it once for 1s, and then do the sweep, but whatever. This way worked for me. So anyway, yeah, I enjoyed the problems. I hope you guys enjoyed them as well. I thought it was a good contest. Thanks to Vuv and Mike, or Vovu and Mike, for the problems. Thanks to Mike for the Polygon platform. And I hope your rating went up if it was rated for you, or I guess hope you enjoyed the problems as much as I did if it wasn't. So that's all. Thanks for watching, and goodbye.